Okay, let's look at some examples. Well, let's look at the first. Let's look at maybe one of the examples here. Let's consider on. Let me see. This is page 285 in the text. Problem 17. Well, let's see. We can. This is a die is rolled twice. Okay, if a die is rolled twice, then well, we know the sample space is easy to see. It is H H H, heads, tails, tails, heads, tails, tails. Oh no, it's not a dice. It's not a coin. I was going to write down a coin. This is a dice. So and since we don't specify the number of sides, I think we're going to give this, the sample space is, if I roll one dice, the numbers are 1 through 6. So the sample space is going to look like 1 1 1 2 ... 2 1 2 2 ... up to 6 6, where we label the outcomes as the outcome on the first die, the outcome on the second die. So the size of the sample space is going to be, well, the first dice can have any of 6 possibilities. The second dice can have any of 6 possibilities. The total number of possibilities, because the two outcomes are independent of each other, is going to be 36. So, and it asks, what's the probability the sum of the faces is greater than 7? Okay, so this seems like a hard problem. So we have the event where the sum is greater than 7. Well, this is the problem is given, but given that, so we're asked for a condition, given that first outcome is a 4. Okay, this is item 1, is we want to know the probability that the sum of the 2 dice is greater than 4. Now, the sum of the 2 dice, what are the possible what this event is going to equal 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and well, this isn't a good way to say it. Because I'm giving the sum, but that conflicts with the way of writing them up here. It's going to be all outcomes where sum greater than 7. Okay, well, so it's like we could try to write this out and do some fancy counting to figure out, and now how many elements were in this set. But since we only need we're actually being asked for the conditional probability that the sum is greater than 7, given that the event of a 4 occurring. Okay, now what is this? How is this conditional probability defined? Well, it's defined as the probability that the intersection occurs, that the sum is greater than 7, and let's see, this is a little bit ambiguous, not just that a 4 occurs, for first event that 4 first, okay, over the not the sample space size, but the event, the number of ways that you can have a 4 first. Okay. So this is just applying the definition of conditional probability, and then we can analyze this a little bit to see what we need to solve this problem. Well, first of all, that the intersection of a 4 first and greater than 7, we can look and see, first of all, what is this, what are the outcomes in this event? E greater than 7, intersection 4 first. Maybe it's going to be easy to count these because this is going to be sort of 4, and then we have to have 7 or larger, right? Because, or maybe it's going to be hard to count, but at least we can get a handle because we can have 4, 3, because that's 7, 4, 4, 4, 5, 4, 6. Then we'd have to go up to, but there has to be a 4 first, right? So we have to have a 4 here. So it could be 4, 3, 4, 4, 4, 5, 4, 6. Those are the only ones where the sum is 7. Well, if it's, let's see, is it 7 is greater than 7? That actually lets out this one because it's going to be greater than 7, not just greater than or equal to 7. So it looks like those are the only 3 elements that are in here, right? 8, the sum is 8, 9, and 10. And if you have a first, that's all that can possibly be. And how many different ones are there for the event of 4 first? Well, that's going to be 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Okay, so the conditional, the probability that the sum is greater than 7 with the event of 4 first is going to equal basically the number that are in this intersection over the number that are in the event of 4 first, which looks like it's equal to 3 over 1, 2, 3, 4, 5, 6, 6, which equals 1/2. So half the time, and you can see that from this here, that if you know that a 4 first has occurred, these are the possible things you're looking at, and half of them, this half has the sum greater than 7 and half or less. So that is, you know, the first outcome was greater than a 4. And so we can just do the explicit counting. Now, we could just to try to see if we could do it using the law of total probability, more to explain the law of total probability than to make this easier, is could we calculate either of these using the law of total probability? Well, we could, because here we did explicit counting, and I think that if we, because here we reduced it to these a counting problem, but if we didn't reduce it to a counting problem, we'd have to do the probability, and it's not clear exactly how that would work. It's not clear that there's a good division. I mean, we could divide it, for example, into 4 first, 4 not first. So we could have or we could, let's see, I think we could, yeah, that might be one possibility. And that, and that would, let's see how that would work. If we, well, basically what that would mean is we'd use the definition of here of probabilities, the probability that E greater than 7 intersection E for first. Well, let me, okay, so then what, we're going to divide up S into E for, can't spell first exactly. Okay, 4 first, union E, other first. So something sort of like either 4 is first or 4 is not first. So those are sort of a set and its complement. Then I know that this probability of the intersection is going to equal the probability that of the event greater than 7 and 4 first, awkward to write, given that E 4 first occurs, times the probability of E 4 first, plus the probability of E greater than 7 and 4 first, times the probability that E other first. Okay, so it divides into these two halves. So then what is this equal to? I'm calculating this probability here. So it's the probability that the event occurs times, this is sort of, there's two events in the partition. Well, the probability that the 4 first, given that the 4 first occurs, this is going to be 1 because it's always going to be the case that if the 4 first has occurred and it's greater than 7, then the 4 first has occurred times the probability that you have E 4 first occurred plus, what's the probability that you have E greater than 7 with 4 first and the other occurred? Well, that's going to be 0 times the probability that E other occurred. Now, the probability that E first occurred, let's see, how have I, there's some, let me just pause the recording for a second. Okay, there was a momentary misunderstanding there on my part. We're calculating, this is what the error was here. Those aren't equal. This is equal to this. We're just calculating here the probability of the intersection. And that's what we can use, the total probability. So these one isn't equal to this. That was the sort of mistake I made to set this up, but everything else is okay. So these two, this is a partition, this is equal to this is equal to this. And so we have the intersection equaling 0 times the probability, 1 times the probability that E first occurs, 0 times the probability that it's the first one is other than 4. And so this is going to equal just the probability that E 4 first occurs, which equals the number of elements where you have a 4 first, which is these 6 elements, divided by the sample space size of 36, which equals 1/6. And that gives you the probability of the intersection, 1 in 6, which is okay. But then we want to, if we want to calculate the probability that the okay, I still have a problem. Let me since I have made a mess of this, let me pause this back. Okay, so I'll figure out this what the bug in my thinking was up here, and we'll continue with that next time, and I'll write it out for you and put it on Piazza. Okay, so if we continue with problem 17, number 2, the calculation of the conditional probability is fine. It's just that there's something between here that's a question mark that I want to sort of not have to work through and waste your time on. Okay, so number 2 was, we want to know that the probability that of the event of greater than 7, given that we have first outcome greater than 3 first. Okay, so that the first outcome is greater than 3. So that's how can we, the problem with, let's first write the definition. This conditional probability is going to equal the probability that the sum was greater than 7 and intersected with the event that the let me write this differently. First greater than 3, there it is. That the first greater than 3. So that's not just 4, but it could be 4. So the first one could be a 4, 5, or 6. So there's more possibilities here. And divided by the probability of E first greater than 3. Okay, well, let's see if we can figure out how to calculate then each of these total probabilities. In other words, we need the ratio to get the conditional probability that the sum is greater than 7, given that the first one is a 3. So we're asking, okay, we know that the first one was either a 4, 5, or 6. We know this, and we want to know that the probability that the sum is greater than 7. So, for example, these would include events like it would include events like 4, 4, and 5, 3, and 6, say 2, and lots more in that way also. So, well, there could be, this sort of suggests a natural, since we saw that in the previous one, it wasn't so hard to calculate the probability that a 4 was first. So we could divide it up into a partition. Just calculate this one here. To calculate the probability, let's calculate this first. Of say a 4 first, union E 5 first, union E 6 first. In other words, we've divided it up because there could either be in anything a 4 first, a 5 first, a 6 first, and this would be a 1, 2, 3 first, 1, 2, 3 first. This is sort of anything else. So these are 4 events that are mutually exclusive. Either it's 1, 2, 3, or it's 4, or it's 5, or 6. The first one, and then we want to know what the probability is that that's greater that the first one's greater than 3. So we can divide this up into that the probability, using the law of total probability, the E of the first greater than 3 is going to equal the probability of E first greater than 3, given that the first one is a 4, times the probability of E4F, plus the probability of E first greater than 3, given that E 5F times the probability of E 5F plus the probability of E first greater than 3, given that E6 first times the probability of 6 first. So whether or not this partition is useful or not depends on how easy or hard it is to calculate these things. And for this problem, it may or may not be used. Oh, we have one more, this event here, times the probability of E with a first greater than 3, given that the first one is 1, 2, or 3 first, times the probability of E 1, 2, 3 first. Okay, well, let's see if we can sort out what we know here and what we don't know. So if you want to know that the probability of the what's the conditional probability that the first one is greater than 3 if the first one is a 4? Well, if the first one's a 4, it's absolutely certain that this one is because the event that the first one is a 4 is a subset of or the it is in this this one is this is a subset of the first set. So the probability here is going to be 1 times the probability that you have E4 first plus, well, this is also true. This is a 5 first. So the probability that the first one is greater than 3, given that the 5 is first, is going to be 1 times the probability of E5 first. Plus again, well, if I have the probability that the first is greater than 3, if we know the first one's a 6, it's going to be 1 times the probability that E6 is first. Plus, well, this one, the probability that the first one's greater than 3, if the first one is a 1, 2, or 3, well, that's never going to occur. That's got to be 0, because essentially these are, the intersection here is the empty set. So basically, there is a subset. We've chosen the partition, fortunately, where the relationship between these two events is either a subset relation, so you have 1, 1, 1, or the intersection is the null set, so you get 0. Then it doesn't matter what this last probably 1, 2, 3 F is. Okay, so we know that this probability equals the sum of these 3. Well, from looking up this first one, we calculated that the probability of E for a 4 first, let's just repeat that then. The probability of E4 first equals the number of outcomes where there's a 4 first over the sample space size. Well, this one is going to be the number of elements in the set 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, right? Over 6 times 6 is 36. Well, there's, if a 4 first, the second one is then independent. So that's 6, right? And then the probability that E5 first equals the number of where there's a 5 first over the sample space size, but this is going to be the same number because you just have 5, 5, 5s here in the first one, but you're still going to have any one of this is going to be 6 over 36 equals 1/6, and probability of E6 first equals 6 over 36, which equals 1/6. So the probability that the first one is greater than a 3 is going to equal 1/6 plus 1/6 plus 1/6 equals 3/6 equals a half. And then we could go back and check. Like if you try to sort of look at, you might want to check that that this makes sense in terms of the fact that, well, that the first one could be 4, 5, or 6. And if it's not 4, 5, or 6, it's 1, 2, or 3. And you can sort of see that half of them are going to be with the first one greater than 3 and half less. And so that corresponds to this 1/2.